Hello, everyone. So today we're going to be continuing our conversation on electrochemistry to talk about how we can use electrochemical observations of a electronic cell to determine our good old friend of thermodynamic functions. So a good place to start would be, say, thinking of some case like our lead acid battery. And then we're going to try and figure out how we can measure all of the various thermodynamic functions of this process. So a good place to start is our Gibbs free energy reaction. So we can figure out the Gibbs free energy of the reaction being measured by the cell simply by using unit conversion and taking our measured potential and turning it into a Gibbs free energy of reaction. And this is actually a fairly straightforward process. However, as you can imagine, Gibbs isn't the only thermodynamic function we care about. We also want to say determine entropy and enthalpy. So a good place to start would be to examine how our Gibbs free energy reaction changes with temperature. So if we go back to our good old friend, the fundamental equation of thermodynamics, which may have been a long time ago, but from there we observed that the temperature dependence of our Gibbs is simply going to be entropy. And since we're looking at the Gibbs of reaction, consequently, we'll end up getting a relationship to the entropy of reaction. So again, simply by measuring how our Gibbs free energy changes with temperature, we can get the negative of the entropy of reaction. However, we can then go ahead and pair these two equations together. So what we then find is that the negative of our Gibbs free energy of reaction is simply going to be the derivative of NFE with temperature. Well, here we run into the beautiful little bit that N is going to be a constant built into the chemical reaction, in this case 2, and Faraday's constant is a constant. So I can go ahead and pull both of those out, and you'll notice that we now have no negative signs. So I'll go ahead and move my electron coefficient and my Faraday's constant over to the right-hand side of the equation. And when we do this, we find that if I'm able to determine how the chemical potential changes with temperature, then congratulations, the slope of that line is going to give me the entropy of reaction. Again, once I account for the stoichiometry and unit conversion. So doing that, I end up determining two of my three thermodynamic functions. I can quickly measure my Gibbs free energy of reaction and my entropy of reaction. That only leaves me with one thermodynamic function left, and that would be enthalpy. So from here, we can use our basic definition of the enthalpy of reaction simply as the Gibbs of reaction plus the entropy of reaction times the temperature. So when we do this, we can then substitute in our two expressions. Again, negative NFE for Gibbs and NF times the temperature dependence of the potential for our entropy of reaction. So when we do this, you're going to notice, let's be honest, there's a lot of NF terms here. So we can go ahead and collect them together. And we'll go ahead and pull out a negative sign. So when we do that, all we're left with is the potential of the reaction and now a negative, because I pull out a negative sign, of the temperature times the slope of the electrode potential with temperature. So this means that if I do a simple measurement of electrochemical potential for reaction over multiple temperatures, I can go ahead and more or less take my potential and then subtract out this gradient term, and this will let me determine the enthalpy, entropy, and Gibbs free energy of reaction. And this is an incredibly powerful set of tools, which provides a good source of how we can determine the thermodynamic functions for a set of redox reactions. And consequently, once I have the Gibbs free energy, enthalpy, and entropy of reaction, this gives me a sort of reference point that I can determine non-redox reactions entropies and enthalpies to compare to. So this is a good source of how we can build up our thermodynamical knowledge. However, it is worth noting that so far we're just considering full redox reactions. So next time we're going to look in a little bit more detail at those half reactions we described earlier and what sort of information I can get out of those. Until then, take care.